we proved that Mobius maps take generalized circles. So generalized circles are basically straight lines and circles. I'm calling them generalized circles to generalized circles. Yeah, so Mobius maps take straight lines and circles to straight lines and circles. Then we constructed two examples of Mobius maps. By examples, I mean the following. So we mapped, so the principles to keep in mind are that if you specify where three distinct points go, then you have uniquely fixed your Mobius map. You don't have any more freedom, okay, firstly. Secondly, suppose you specify 3 points and their images lie on a straight line, then the line containing those three, suppose these 3 points are on a circle or on a straight line, that thing goes to the straight line. Okay, that's one thing. The other thing is Mobius maps take the interior of a circle, or for instance, one half of the plane. If you give me a straight line, one part of the plane goes to the interior of, suppose this goes to a circle, then this goes either to the interior or to the exterior. Okay, likewise for the other half. All right, so these were the basic principles that we used. Yeah. So the thing is, we mapped the upper half plane to the unit disk using a Mobius map. Yeah. So we first mapped this to the circle. We made sure that at least one point here went to a point here, and therefore that did the job. We did something more complicated. We took this hemi-disk and mapped it to this disk. How did we do that? The idea is to first map this using a Mobius map to a sector like this. Then use z going to z square to map it to the upper half plane, and then you have the previous example gives you a map from the upper half plane into the disk. Okay. So the point of these examples is to tell you that not everything can be done by Mobius maps. You might have to do things like this. That's one thing. The other thing is also to show little tricks that you can use to find the maps that you want. Okay. We then proved that Mobius maps are precisely the automorphisms of the Riemann sphere. What does that mean? If I give you a Mobius map, it defines a map from the Riemann sphere to itself, right? And it's a one-to-one conformal map of the Riemann sphere to itself. In other words, it's an automorphism of the Riemann sphere. If I take any automorphism of the Riemann sphere, then this must be a Mobius map. This is what we proved. Okay. One direction is easy, proving that this defines a map from the Riemann sphere to itself. The harder direction is anything, any conformal map, one-to-one conformal map from, so any conformal map from the Riemann sphere to itself is indeed a Mobius transformation. That requires some work, and we proved that. Okay. Yeah.
Sir, sir,
Yeah.
here automorphism means bijective and analytic map.
Yeah, basically.
Okay.
Except that when you talk about analytic maps from the Riemann sphere to itself, what you actually mean is meromorphic functions from C to C that are one-to-one, such that f of 1 by z is also a one-to-one meromorphic function. Okay?
Yeah, okay.
Okay. Then we also proved that Mobius maps with real coefficients. That means things like this. where A, B, C, and D are all real, and satisfying AD minus BC equals 1, mapped the upper half plane to itself. Okay, so Mobius map, the only Mobius maps that conformally map the upper half plane to itself are those that have real coefficients and satisfy this. Okay, so that's what we proved. All right. In the homework, you will verify that these particular kinds of Mobius transformations form a subgroup of the Mobius group. What that means is, if you take maps of this type where A, B, C, and D are real, and AD minus BC is, say, positive, you can scale them so that AD minus BC becomes 1. Okay. If you take these sorts of Mobius maps, they actually form a subgroup of the entire Mobius group. In other words, if you take these sorts of Mobius maps and you compose them, you get similar Mobius maps. If you, the inverse of this sort of a Mobius map is also of this type. Yeah, these are the only things that are necessary. And Z goes to Z is such a map. Okay. Moreover, given any point Z equals x plus iy, where y is positive, that means you're in the upper half plane, there exists such a Mobius map taking it to I. What does this mean? That means if I take the upper half plane and if I take any point here, there is a Mobius map mapping the upper half plane to itself that takes this to this. In other words, there exists a Mobius map of the type AZ plus B divided by CZ plus D, where A, B, C, D are real and AD minus BC is positive, such that if I call this f of this particular thing, f of x plus iy equals I. For this particular value. Maybe I should have called this x naught and y naught. Maybe then it will be x naught plus iy naught is I. Okay. So this is the statement. I hope the statement is clear. In particular, we proved earlier that given any 3 points, you can take them to any 3 other points using a Mobius map, right? What is the difference between that statement and this statement? Why is this not a trivial consequence of that statement? Let me repeat myself. In the last lecture, we proved, maybe in the last of the lecture before that, that given any 3 points in the complex plane, there exists a Mobius map taking these 3 points to any 3 other points on the complex plane. Here, I simply seem to require 1 point to go to one other point, namely to I. I mean, why is this not a special case of the earlier result? Why am I mentioning it separately? Any thoughts? Is my question clear?
Yes, sir. Question is clear.
Right.
So basically, upper half plane to upper half plane and n is z to I.
Yeah. So my point is, why does it not follow from the earlier result where we said any 3 points can go to any 3 other points by means of a Mobius map? That seems to have proven something even better, right?
Yes.
So what's the catch?
In that one, we used to map line to a line, right? Real axis to a real axis. Here we are taking some point in the upper half plane.
No. In the previous result, I'll tell you what the previous result states. The previous result states that given any three points in the complex plane, I can find a Mobius transformation that takes these 3 points to 3 other points, any 3 other points on the complex plane. Okay, that's the previous result.
Here we are fixing I on the right hand side. But there it was any 3 points.
No. I mean, the earlier result was given any 3 distinct points, I can take them to any 3 other points using a Mobius transformation. In particular, I can take this one to I if I want to. Right? So given 1 point, I can surely take it to I using a Mobius transformation. Then what is different about this result? I seem to be proving something even better, right? Not only can I take this point to I can take these two to other points simultaneously.
A, B, C, D are real.
That is the point, exactly. Because a Mobius map of this type need not take the upper half plane to itself, no? For example, if I take any general Mobius map, it can take the upper half plane to the unit disk, no less. What we want is we want to take the upper half plane to itself and we want Z to go to I. Z naught if you wish to go to I. In other words, we want A, B, C, and D to be real and for this to happen. That is not guaranteed by the previous result. I hope people appreciate this fact. This is not. So that's why this result is not trivial. It requires a proof. Oops. All right. So suppose we want AZ plus B by CZ plus D equals I and ABCD to be real, then. So you can cross multiply on both sides. Therefore, if you write Z as X plus IY, you'll get A times X plus IY plus B is IC times X plus IY plus ID. Now, these are all real. These are all real. So you can compare the real and imaginary parts, right? Let's see. X plus B plus IY is minus CY plus I times CX plus D. These are all real. So you can compare the real part. So that means this equals this. You can compare the imaginary part. So this equals this. So you get these two equations. Yeah? Here, you can say that C equals this. You might wonder what happens when y is 0. Y is not allowed to be 0 because we are looking at the upper half plane. So no problem. Yeah. Once you have C, you can substitute it here and you can solve for D, for example. You can say it's AY plus this. Moreover, AD minus BC is whatever this is. This is always positive if A is non-zero, for example. So if we choose some nice numbers, then this does the job. This does what you want. Okay. It's an easy proof, but it needs to be proven, right? Okay, so let's move on.
So,
Yeah.
sir, not only I, we can map to any other point, any complex number to any point.
Absolutely, absolutely. You're right. So the fact that these things form a group, that means if I take any such Mobius map where A, B, C, D are real, then its inverse is also a Mobius map where A, B, C, D are real. So the point is, if I want to map Z to W, I'll map Z to I. then I'll map I to W. I mean, I can map W to I, just take the inverse of it, that'll take I to W, and compose these two. Okay? Yes. Right. So, since the upper half plane is conformally equivalent to the unit disk, what does this phrase mean? That simply means there is a conformal map from the upper half plane to the unit disk. By using this particular conformal map, the Mobius automorphisms of the disk, what does that mean? What are all the Mobius maps that take the unit disk to itself? You don't have to work this out separately because you already know what are all the Mobius maps that take the upper half plane to itself. They are all of the type AZ plus B by CZ plus D, where A, B, C, D are real and AD minus BC is positive, right? So what about the disk to itself? You can map this to this. I mean, you can map this to this first, this to this first, and this to this first. Those are precisely all the Mobius transformations that take the disk to itself. In other words, they're all of this type, sigma F sigma inverse, where F is a Mobius automorphism of the upper half plane. Okay? Right. So, yeah. So there's a neat little result. So we know exactly what the Mobius maps that take the disk to itself, the unit disk to itself are. They're precisely of this form. Okay. In this way, we can take any point on the disk to any other point on the disk by means of a Mobius map. So if I give you any, yeah, a question, comment?
I think there is no question.
Oh,
From disturbance.
sorry.
Thank you.
So if you take any point on the disk, and if you want to map it to some other point, all you can do is first of all, map this to the upper half plane. This will go somewhere, right, to some z tilde. Map that, map this also to the upper half plane. This will go to some other point w tilde. And there is a Mobius map taking this to this. Okay, there's a Mobius map taking this to this, there's a Mobius map taking this to this, right? So you can take the inverse of this. So this whole, you go from here to here, here to here, and then here to here. The composition of these three maps is a Mobius map that takes this to this, okay? So you can take any point inside the unit disk to any other point by means of a Mobius map. The Mobius maps are very powerful. There are so many Mobius maps that you can accomplish this task. Okay? The real question is every automorphism of this form? What does this question mean? So what's the meaning of this question?
So means any map bijective and analytic map from unit disk to unit disk is composition is a Mobius maps. Only Mobius maps.
Exactly. Okay. Good. So the question is if I give you any one-to-one analytic function from the unit disk to the unit disk, is it necessarily a Mobius transformation? And if it is a Mobius transformation, it has to be of this very specific type. But anyway, that aside, the point is it a Mobius transformation? We have already answered and asked and answered a question of this sort earlier with regard to the Riemann sphere. Any automorphism of the Riemann sphere must be a Mobius map. Does the same hold true for the unit disk? or for the upper half plane, whichever, because both are conformally equivalent by means of a Mobius map. Okay. So this is the question we want to answer. The answer is fortunately yes. In other words, every one-to-one analytic map taking the unit list to itself must be a Mobius map. That is why Mobius maps are so important, because they tell you exactly what the automorphisms of the unit disk or the Riemann sphere are. Okay. So how does one prove it? To prove such a result, we need a useful lemma. Now, once again, since someone asked me this question, what's the difference between lemmas, propositions, theorems, etc.? This lemma, Schwarz's lemma, it's a lemma not because it's an easy result. Easier results are often called propositions. Corollaries are very trivial consequences of theorems or propositions. So this is a lemma. This is not a trivial result, but the point is it's so useful that it is used everywhere, all over the place. That's why it's a lemma. Okay. Theorems are usually things that come at the end of the book, in a sense. Lemmas, on the other hand, do all the heavy lifting in mathematics. They are like spanners or hammers, if you will. Okay. So this lemma, Schwarz's lemma, is as follows. Let f from the unit disk, from the open unit disk to the complex plane, let this be a holomorphic function. Yeah? Such that f of 0 is 0 and mod f of z is less than or equal to 1. Okay? So f from the unit disk to the complex plane is a holomorphic function that in fact takes this to this. That is, the image of this is somewhere here. 0 goes to 0. Okay? And all of mod of z, f of z is less than or equal to 1, which means the image is somewhere here. Okay? Then the result is mod f of z is less than or equal to mod z for all z in the disk. And mod f prime 0 is less than or equal to 1. So the idea behind the intuition behind this statement is, if you have a map that takes 0 to 0, this whole thing goes inside this. So if the derivative here is too large, that means all these points nearby are allowed to move by a huge amount, right? So that is why there's this is saying that they're not allowed to move too much. And mod f of z is less than or equal to mod z. There's no real intuition for this. Okay. All right. I hope the statement of the lemma is clear. It might look like this lemma is very technical and it might not be useful at all, right? But we'll see in a moment as to how it can be useful. So in particular, yeah.
So sir, mod of f dash 0 is scaling up the points near 0.
I'm not saying that. I am saying the derivative tells you roughly the rate of change, right? So if the derivative at 0 is very high, that means points near 0 probably move a lot, right? It's just very rough intuition. I'm not making this precise at all, okay? Please don't take it very seriously. I'm merely saying this is roughly, very roughly saying that points near z equals near 0 don't move much. And they shouldn't, right? Because there's only a limit as to how much they can move. They can't move more than, I mean, all the points here have to fall here, right? They can't move outside the disk. So I'm just trying to motivate this statement. Don't take it too seriously. Don't take it literally, okay?
Okay, sir.
Yeah.
And the map is from unit disk to unit disk only, not
More or less, yeah, because of this condition, it's unit disk to unit disk, except on paper, one of these can go to the boundary on paper, right? Because it's less than or equal to 1, not strictly less than 1.
But the result says mod fz should be less equals to mod z for all z belongs to D. So it will become within the interior of the disk, right?
Yeah, but that is a consequence. That is not an assumption. That is a consequence of the assumptions. That's the theorem, right?
Okay, so ultimately we can have the image inside.
Yes, absolutely, absolutely. Okay, good. If mod f of z is equal to mod z for some z not equal to 0. Of course, f of 0 is already 0. That's not the point. For any other z, if this is true, or if f prime of 0 mod is equal to 1, then f of z is very simple. It's just a rotation. Okay. Excuse me. Sorry. So, the Schwartz lemma is saying something very strong. It says, for example, it implies that if f of 0 is 0, and let's say, for example, f of half is half, that means f of z is z, right? It's the identity map. So if it's fixing 2 points, it has already become identity, right? How do you explain this phenomenon? So my point is, recall that in general, if I don't care about fixing the unit disk, if I take any general map from Mobius, any general Mobius map from the upper half, from complex plane to itself, it can take any 3 points to any 3 other points, because there are 3 complex parameters, 3 free parameters, right, in a Mobius map. However, in the case of the disk or the upper half plane, there are only 3 real free parameters, right? In other words, if you already fix 1 point, that means you've used up 2 real free parameters. You have only 1 at your disposal. If you fix 1 more point, that's it. You have nothing, right? So there's no shock. It is not shocking that such a result is true. Okay. I hope the statement of this result is clear, okay, before we go on to its proof.
So how we are fixing 3 points here?
You are not. What I'm trying to say is the following. So what is this saying? If mod f of z equals mod z, or if mod f prime 0 equals 1, then f of z is a rotation, right? So what I am trying to say is that if you have a map from the unit disk to itself, right, that takes f of 0 to 0. So let us, for example, let us only look, for instance, let us look at Mobius maps. Suppose we look at the special case. Mobius maps that take the disk to itself. How many free parameters do you have? You have 3 real free parameters. Why? Because they're of the form, I mean, at least for the upper half plane to itself, they are of a very specific form, az plus b by cz plus d, where a, b, c, d are real and ad minus bc is positive. What about the disk to itself? You first map this to the upper half plane, then the upper half plane to itself, and back to the disk, right? So there are only 3 real free parameters at your disposal. If you want to fix the origin, if you want to take 0 to 0, you have already used two parameters because you're taking a complex number to itself, right? Or if you wish, you're taking a real number to itself. So maybe you might think you've already used maybe one real parameter. What if you make sure that, if you also in addition make sure this or this happens, that means you would have used one more real free parameter and you'll be left with only one at your disposal. And that's what this is saying. F of z is e raised to I theta times z, where this is your third real free parameter. So this is giving some intuition as to why this sort of a statement is expected. Once again, it is not a proof, it is not something to be taken too seriously, it's just to give you some intuition. Okay. So I hope this statement of Schwarz's lemma is clear. Okay. Any questions about the statement before we move on to the proof? All right, so let's move on. Assuming this lemma holds true, we can prove that every automorphism of the unit disk is a Mobius map. What is our goal? Why did we start discussing Schwarz's lemma? Because we wanted to answer this question in the affirmative. Okay. So how does one prove this assuming Schwarz's lemma? Indeed, suppose f from the unit disk to itself is an automorphism. Then by composing it with a Mobius map, we can assume without loss of generality that f of 0 is 0. What is the meaning of this phrase and why is this true?
Consider the image of f of 0 to be alpha. Then we can identify a Mobius map such that this alpha goes to 0.
Very good.
Now compose it and say it, the composition itself.
Yes, that's correct. So in other words, suppose you don't have, suppose f of 0 is not 0. If suppose f of 0 is alpha, then alpha can be made to go to 0 by means of a Mobius map that takes the disk to itself, because we just proved that, right? You always have a Mobius map taking the disk to itself that takes any point in the disk to any other point, in particular alpha to 0. So if you compose these two maps, the new map will now satisfy f of 0 is 0. And suppose you manage to prove that this new map is a Mobius map, then the old map should have been 1, 2. Okay? All right. By Schwarz's lemma, if f of 0 is 0 and f takes the disk to the disk, we have satisfied all the conditions necessary for Schwarz's lemma. So we can apply Schwarz's lemma and conclude that f prime 0 mod is less than or equal to 1. And here comes the neat trick. Because f is an automorphism, f inverse is also analytic. F inverse takes 0 to 0 and f inverse takes the disk to the disk. So f inverse also satisfies the hypotheses of Schwarz's lemma. Okay? In other words, the derivative of the inverse at 0, the modulus of that is also less than or equal to 1 according to Schwarz's lemma. What is the relationship between the derivative of the inverse and the derivative of the original function? Even in one variable calculus, how do you find the derivative of the inverse of a function? If it exists.
By the inverse function rule, sir? 1 by f prime or something.
Yes, that's correct. So in other words, basically, f of f inverse of z is z. So f prime of, by the chain rule, f inverse prime of z is identity. So f inverse prime of z is 1 by f prime of f inverse z. Yeah, this is what you were referring to, hope, right? So,
Yes, sir. Yes.
okay, good. So suppose I substitute 0 here, I'll get this, but f inverse of 0 is also 0. So this is 1 by f prime of 0, which means, so t prime 0 is 1 by f prime 0, but that's a contradiction. Why? Because f prime 0 is less than or equal to 1, which means 1 by mod f prime 0 is larger than or equal to 1. But this is mod of g prime 0, but we are saying this better be less than or equal to 1. So the only possibility is if this is equal to 1. But if f prime of 0 equals 1, according to Schwarz's lemma, f of z is a rotation. It is a times z. Yeah? In other words, f is a Mobius map. So we are done. Okay? Very quick proof. Very, very quick proof. And all the magic happens because of Schwarz's lemma. Okay? And as I said, for example, another thing is if f of 0 is 0 and f of half is half, and f takes the unit disk to the unit disk, it's an analytic map that does this, then f of z has to be z, for instance, by Schwarz's lemma. Okay, there are lots of applications of Schwarz's lemma. Okay, so it's a very fundamental result. All right, so let's try to see how to prove Schwarz's lemma. Once again, the key point here is the maximum modulus principle. You need to apply the maximum modulus principle to a cleverly chosen function. So define h of z to be f of z by z when z is not 0. And when z is 0, what should I define it to be?
Derivative.
Dash 0.
F dash 0. Why? Why should I define it to be f dash 0?
Sir, if we take a limit z tends to 0 of hz,
Yeah.
that will give me, it should be f dash 0.
Yeah, because f of 0 is 0. Right. Okay. So this function is holomorphic. I mean, you don't need to use anything fancy. So how do you prove that h of z is holomorphic? Well, of course, f of z by z is holomorphic everywhere except at z equals 0, possibly, right? That's the only thing that can possibly go wrong, because whenever z is non-zero, the ratio of two holomorphic functions when the denominator is non-zero is holomorphic. So what can happen at z equals 0? Let us see that it is indeed complex differentiable. So this is f of 0 plus h by 0 plus h minus f of f prime 0 divided by h, right? So this is f of h by h minus f prime 0 times h divided by h squared, limit as h approaches 0. Why does this limit exist? Let me write the limit again. I'm sorry, it is f of h minus f prime 0 times h divided by h squared. Why does this limit exist?
Because it takes 0 by 0 form.
So that doesn't mean the limit exists. H by h square is also of the 0 by 0 form.
The same as f prime of 0, right?
Not quite. Because I already have f. Notice I'm dividing by h square.
Okay, sir.
Sir, f is analytic, so we can expand by Taylor's theorem, sir.
Yeah. So you write the power series for f of h. So that is f of 0 plus h f prime 0 plus h square by 2 factorial f double prime 0, etc. This is 0. So if I substitute this here, f of h minus f prime 0 times h, this is h square by 2 factorial f double prime 0 plus blah, 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 and then you divide by h square. And then these two get cancelled and everything else has an h times something. So this goes to 0. And this is f double prime by 2. Okay. Right. So this is basically, it not only exists, it's f double prime 0 by 2. All right.
Sir. Sir, from where you get this ratio fh minus f dash 0h upon h square?
So what am I trying to do there, right? What I'm saying is, I want to, so let me just erase this. So I want to prove this statement. I want to prove that h of z is holomorphic. I'm sorry, the letter h has been used too many times. That was my mistake. I want to prove this function is holomorphic. It is, of course, analytic when z is non-zero, because the ratio of two holomorphic functions, as long as the denominator is non-zero, is holomorphic. The question is whether it is differentiable, complex differentiable, even at z equals 0. I wrote something fancy here, by the way. If you don't know what these words mean, ignore them. But you can do it in an elementary way also. So the aim is to prove h of z is analytic. H of z is surely analytic when, say, in fact, why do all of this? I can do it even more simply. F of z is an analytic function, so it is f of 0 plus z times f prime 0 plus so on. And when you divide by z, f of 0 is 0. So this is simply f prime 0 plus z by 2 factorial f double prime 0 and so on. Okay, so this is a power series which is convergent. So this is already analytic. You don't need anything fancy, actually. It's very easy. All I wanted to prove is that this is, the problem is h of 0 is f prime 0. So if I say h of z is z, if this when z is non-zero and h of 0 is f prime 0, then h of z is precisely this power series, so it is analytic. I just wanted to prove it's analytic, that's all. Maybe I overcomplicated this. Okay. Yeah?
So, you have written, so if we want to use Modulus theorem, then we need to show that integration over any triangle will be 0. Right? So how to get from this statement?
Well, if you take any so it's holomorphic away from z equals 0, right? So the only thing that can go wrong is if you take a triangle that either contains 0 or passes through 0, right?
Yes.
But if it does pass through 0, it's after all continuous at 0. So what you can do is you can take instead of this triangle, what you can do is you can take a slightly smaller triangle. Over here, the integral is 0. So the integral that you need is only the integral over this small triangle. Likewise, here also, if you take the integral over this triangle, that boils down to an integral over a smaller triangle. If you split it up into three integrals, right? These three triangles are of this type. So in other words, if you take this very small triangle, this integral can be made as small as you want by choosing the triangle to be small enough. Okay.
Yes.
But anyway, this is too fancy. It's much simpler than that. So please ignore this statement and the previous statements. It is very simple. Okay. All right. So the point is, this function is holomorphic. Therefore, you can use the maximum modulus principle. What does the maximum modulus principle state? That so this function is defined on the unit disk, right? H is defined on the unit disk. So if I take any circle of radius r, right, the maximum on this circle is on this disk of radius r is attained on this circle. So the value of h of z anywhere in this region is less than the maximum over this circle. And what is the maximum over this circle? It is simply the maximum of mod f of z by mod z over a circle of radius r. And so this is equal to r. And f of z, mod f of z is less than or equal to 1. So in other words, this is less than or equal to 1 by r for any r less than 1. Is this clear? Okay. So this means that h of z is less than, mod of h of z is less than or equal to 1. Why? Because suppose mod of h of z is strictly larger than 1, then surely you can find a contradiction using this. You can find some r where r is less than 1, which is close enough to 1, that will contradict that statement. So this is the case. Okay. So that already proves one part of Schwarz's lemma, actually. So mod f of z is less than or equal to mod z. Okay, so that proves one part of Schwarz's lemma. In fact, since mod h of z is less than or equal to 1 for all z, so that means mod h of 0 is less than or equal to 1. This means that mod f prime 0 is less than or equal to 1. So this proves one more part of Schwarz's lemma. So the real point is, what happens if equality holds in either of these two inequalities somewhere? So if mod f of z naught equals mod z naught holds for some non-zero z naught, or if mod f prime 0, which is h of 0 mod equals 1, that means mod h of z naught equals 1 for some z naught. Okay. So if mod of h of z naught equals 1 for some z naught, that means the maximum modulus principle. So what does the maximum modulus principle state? It states that if the maximum is attained inside, then h is a constant. Very good. Right? So mod h of z is less than or equal to 1 throughout the open unit disk. At some point inside it is attaining a maximum, that means h is a constant. Therefore, h of z is a constant a, which means f of z equals az for some a whose modulus is equal to 1. This is the proof of Schwarz's lemma. Once again, the key ingredient in this proof is the maximum modulus principle. And this proof should remind you of an earlier proof where we proved that the automorphisms of the Riemann sphere are Mobius transformations. Even in that proof, some function like this played a very crucial role, right? So, right. So this is the proof of Schwarz's lemma, right? So let's move on. Okay, so non-examples of mapping to the disk. What am I saying? So we note something curious. Using our examples of, yeah?
So sir, automorphism of unit disk to itself has the coefficient ABCD all reals?
No. From the upper half plane to itself has all reals. From the unit disk to itself, if you want to get the automorphisms, you first map the unit disk to the upper half plane by means of sigma, where sigma is this.
Yes.
And then by sigma n, you have to do this, basically. You map the unit disk to the upper half plane by sigma inverse, then on Mobius automorphism with coefficients are real, and then back by sigma to the unit disk. So the coefficients are not real. All right. So we note something curious. Using our examples of conformal maps, we can conformally map strips, meaning things like this. Using the exponential map, what can we do? We can map this to the upper half plane, for example. Will that work? I think you might have to map this to this, one of these, right? We can map strips, we can map the upper half plane, we can map the hemi-disk, sectors, etc. to the unit disk. In other words, we can map all of these things using some very nice conformal maps to the unit disk. So the question is, what property made this possible? In other words, which domains can you conformally map? Can you conformally map to the unit disk? Why do we care about this question? What is one reason to care about this question? So the reason is the Laplace equation. We know how to solve it explicitly on the unit disk by means of a formula. And if you can map your given domain to the unit disk, you can solve it on that domain also. That's the reason. Okay, so that's why this question is important. So what is something that cannot be mapped conformally to the unit disk? So to answer a question like which domains can be mapped to the unit disk, you have to give me at least one example of something that cannot be mapped conformally to the unit disk. Then we can see what is actually going wrong. Yeah. So the punctured disk cannot be mapped conformally to the unit disk. Indeed, if this was possible, then consider the circle of radius. So what is a punctured disk? Simply the unit disk except for this point. And if this could be mapped conformally to the unit disk, consider a circle of radius half centered at the origin in the punctured disk. The integral of 1 by z over it. If I take a circle of radius half and I try to integrate 1 by z dz over this circle of radius half, what will I get? What will I get?
It's 2 pi.
Yeah, exactly. Right? Because this is equal to 1. That's Cauchy's formula. I mean, you can actually do it explicitly, right? It's 2 pi I, sorry, I forgot the I, okay? So suppose, on the other hand, if this could be mapped conformally to the unit disk, and if F is the mapping, this will go to some other closed curve here, right? Now the point is, the integral of F1 by this function over this weird closed curve, if I take this closed curve, the same function 1 by z will become some other function here. That integral better be 0. Why should it be 0? By Cauchy's theorem, because this is a holomorphic function, right? And the integral of any holomorphic function over a closed curve is 0. But it is not 0. Because if you use a change of variables to actually evaluate the integral, you will see that this answer and this answer should be the same, but one of these gives you 2 pi I, the other gives you 0. So that means that the problem is such a mapping does not exist. Okay? So the punctured disk cannot be mapped conformally to the unit disk. So the problem here is that the punctured disk has a hole at the origin. In other words, if you have a hole at the origin, you can't do this. Okay? So that is what is going wrong. In other words, hopefully, domains that don't have holes, what are other domains that have holes? Things like this. Domains that don't have holes, hopefully we should be able to map them to the unit disk. What if there are no holes? Can we map all of C to the unit disk? All of C doesn't have any holes, right? Can we do that, by the way? Can we map all of C to the unit disk in a conformal manner?
No, sir.
Why not?
Sir, by Liouville's theorem, the map
Exactly.
will be constant.
Very good. The answer is no, because Liouville's theorem. Because suppose you can map all of C to the unit disk by means of a conformal map. In particular, this is a holomorphic function, so it's an entire function, and its domain and its image is surely satisfies this, and a bounded holomorphic function is a constant, but we said it's a conformal map, so it's one-to-one. So that's the problem. Okay, it's non-constant. So then we'll refine our conjecture. Can we map anything that does not have a hole and is not all of C to the unit disk? I mean, sounds like I'm trying too hard, right? Maybe this is also not true, but thankfully the answer is yes. Anything that does not have a hole and is not all of C can be mapped conformally to the unit disk. This is a remarkable theorem due to Riemann. Okay? It's the same Riemann of the Cauchy-Riemann equations. If you've heard of Riemann surfaces, it's the same Riemann. If you've heard of Riemannian geometry or the Riemann hypothesis, it's the same chap. Yeah? So let us make this notion of holes or Riemann integral, same Riemann again. So let's make this notion of holes precise. How do you define a hole? Okay. So domains that don't have holes are called simply connected domains. A hole can be captured by checking whether all loops. So how can I characterize this hole at the origin? Okay. One way is by using this notion of a winding. One way is by doing this, right? By checking if around all closed curves, this is 0 or not. This 1 by z minus a is 0 for all a in the domain. Is this true? If this is true, then it has no holes. Because if it did have a hole, then I could have integrated around the hole, roughly speaking. Not exactly, but roughly speaking, I could have done something like this, and I could have gotten 0. I could have gotten 2 pi I, right? So this is one way to define holes. You simply integrate 1 by z minus a dz over all closed curves for all points a in the domain, and you better get 0. Okay, that is an example. That tells you domains that don't have holes, right? But there's another way to do it. You see, what is going wrong here is, how do you capture a hole? I mean, no matter how small you make it, there's still a hole, right? In other words, if I take this hole, if I fix a point, no matter what curve, if I try to shrink this curve to a point, at some point I'll run into trouble, right? So we can check whether all loops around it can be shrunk to a point. So if I want to see whether something is a hole, we'll take a loop, try to shrink it to a point. At some point, you're in trouble. Oops, there's a problem. Okay. Not by checking whether all loops can be shrunk to a point whilst remaining within the domain. Another way to define, another way to check whether there's a hole or not is to just check whether this is 0 or not. Okay, for all closed curves and for all A within the domain. Okay, right. A domain A, omega, in the complex plane is said to be simply connected if for any continuous closed path 0, 1 to omega, what is a closed path? Gamma of 0 equals gamma of 1. There exists a continuous map. It can be shrunk to a point. How do you make this notion of shrinking precise? That means with time, this should get smaller and smaller and smaller and smaller, right? So this is at time equals 0, this is at time equals 1, right? This is at time equals s. So you have a collection of maps, one for each point of time, right? One for each point of time in omega, so that f of 0t is the original one. At time t equals 0, it's the original map. At time t equals 1, it is simply this fixed point. Okay? And at every point of time, you fix the endpoints are always this fixed point. So in other words, these things look like this. Okay? So domain is said to be simply connected if this happens. Now this definition looks very formidable, right? I can make any definition I want. The problem is, how do I prove, how do I give examples of things that satisfy this definition, and how do I give examples of things that don't satisfy it? This is something that is very important. I've noticed that many students in India lack examples at their disposal. They can all give definitions, probably even prove theorems, but they don't know any single example or a non-example. Okay, that's important. So what are examples and non-examples? Examples, the unit disk. Well, how do you prove that the unit disk is simply connected? We can simply take the following. We can do this thing, right? So suppose you have any loop like this. So just define f of s comma t like this. Gamma of 0 times s plus 1 minus s gamma of t, which means you take gamma of 0, simply connect all these points by means of a straight line to this. Okay, so at every point of time, you get these sorts of curves. And this will always be within the domain. F of st is also within the unit disk. Why? Because of the triangle inequality. Mod of f of st is less than or equal to mod of gamma of 0 times s plus 1 minus s mod of gamma of t. So this is mod of s plus mod of 1 minus s. And in fact, s is between 0 and 1. So this is s plus 1 minus s. This is 1. So this is indeed within this domain. Okay. So the unit disk is an example of a simply connected domain. It does not have any holes. Indeed, if the unit disk was not an example of a simply connected domain, the fault is not with the unit disk, the fault is with us for making a stupid definition. Okay? In fact, any convex open set is simply connected. Do people know what the meaning of this word is? Convex set?
So for any 2 points, if we join the line segment, that also
that lies within that open set, right? So that's a convex set. That is between any 2 points. If I draw a line segment, this lies within this. So what's not an example of a convex set? Something that looks like this. Because if I take these 2 points, if I try to join it by means of a line, oops, I move out of the set, right? So this is not convex, but this is convex. So for any convex open set, you can write this same formula, because this is simply the line segment joining these 2 points, so it lies within this open set. Okay? So convex open sets are simply connected. Now the disk minus the non-negative real axis, this is not convex, obviously, because we join these 2 points, it's going out of this region, but this is still simply connected. This is simply connected. How does one prove this is simply connected?
So if you take any curve inside this, then closed curve, then that will not contain the non-negative real axis, and then we can shrink that.
How will you do it? That's the question. You can't just draw pictures, right? You have to do it rigorously. How will you do it?
So we can take conformal mapping from hemisphere, hemidisk.
What conformal mapping will work?
Z square from hemidisk. And
so this is a conformal map. So how does it help?
So if we take any loop, then it will be a loop in disk.
Very good. Yeah, that's correct. So as he was saying, if I take any loop here using this, and this is a conformal map, that means its inverse is also a holomorphic map. In particular, it's continuous and one-to-one. So if I take any loop here, it becomes a loop here, right? And this is simply connected. Why? Because it's convex, right? So if I can shrink it to a point using this sort of a formula here, and using Z square, I can take that shrinking here. What do I mean? Please write it out carefully. I leave this as an exercise. Okay.
Sir, also by winding number, can we say?
Sorry?
Because by using the winding number, because here the non-negative real axis is not there. Therefore, you can have a analytic log function.
No, but non-negative real axis is not there, so you're saying you'll take a logarithm. Yes, very good. That's also very, very nice. Yeah, that's correct. So using the, I mean, of course, I did not define simply connected by using this so-called winding number, but if I had done it that way, then you're absolutely right. But I defined it this way, so this is the easiest way to prove this. Okay. Indeed, the square root map takes it to the hemidisk, which is convex. Okay. What is a non-example of a simply connected domain? Well, the punctured unit disk is a non-example. So is this, because this is, you can have a conformal map from here to here. So if this is a non-example, even this will be a non-example. If you take an annulus, that's also a non-example. It has a hole. Twice punctured plane, that means if I take C and throw out 2 points, for example. These are all non-examples. Unfortunately, proving that these are non-examples is not that easy. Even proving the punctured disk is not simply connected. That's not that easy. That requires a little bit of work. proving that it is not simply connected. That says, yeah. So I won't do that for you, but and I don't even know if for undergraduates, your undergraduate students do a little bit of topology, but yeah, I suppose if you teach MSc students, they might do a little bit of topology. In that case, you can prove this, but nonetheless, it's important to know the known examples, even if one can't prove it. All right, so the Riemann mapping theorem. Okay, this is the final theorem that I'll mention in this set of lectures. And this is definitely a theorem in the sense that it's very difficult to prove. A simply connected domain, namely a domain roughly speaking that doesn't have holes, that is not all of C, can be conformally mapped onto the unit disk. This is the statement of the theorem. Statement is pretty easy to understand. Moreover, the map is unique up to automorphisms of the unit disk. What does this mean? What is the meaning of that sentence?
So if you take a automorphism from unit disk to itself and compose it with that map, then that will be another map from simply connected domain to unit disk.
That is correct, but that is a very trivial fact, right? That is not what this is saying. This is saying that if you give me any other map from the simply connected domain to the unit disk, that arises by this construction, by composing it with an automorphism of the unit disk. I mean, if I give you two maps from the simply connected domain to the unit disk, the claim is, which are both are conformal maps, both are one-to-one analytic maps. F1 equals F1 composed with F2 inverse. Sorry, you want to go from here. So F2. Sorry, you take here, you go from here to here, and then back. So F2 composed with F1 inverse is a Mobius map. This is what the statement is saying. Okay. So this is the Riemann mapping theorem. This part is actually very easy to prove because if we have two conformal maps, this is going to be an automorphism of the unit disk, and we know that all automorphisms of the unit disk are Mobius maps. Okay, so this is easy to prove. The difficult part is this. Okay. The uniqueness part is straightforward. The existence part, this part, is hard. However, even if I prove this theorem, it's a remarkable theorem of Riemann. What was our original motivation? Our original motivation for this theorem was to solve the Laplace equation. This theorem does not actually directly help with that. Why does it not help? What is missing here? If I want to apply this theorem to solve the Laplace equation on a domain, this doesn't really help. Why? So the point here is, if I want to use this theorem, if I want to solve the Laplace equation on an arbitrary domain, I would need to map it conformally to the unit disk. That part is fine. And this theorem is saying such a map exists. It does not tell you, note that the theorem does not tell us how to find that map. It only says that such a map exists. It doesn't tell you how to find it. It's akin to theology, if you will. Okay. So this theorem is very beautiful, hard to prove. It is completely useless because it doesn't tell you how to find that map. And that is the problem if you want to apply this theorem in practice. In fact, if you give me an arbitrary simply connected domain, there need not even be a very nice formula for such a map. I mean, if it is a very nice domain like a hemi-disk or something, yeah, sure, you can find a nice formula, but you can't always find a nice formula. So the next best thing is that, so it merely says that we can do so. If we want an algorithm that can be implemented on a computer, if you can't find a nice formula to do something, and if you want to apply something to real life, then the best you can do is to get an approximation by using a computer. So you would need a nice algorithm. What should that algorithm do? Given a simply connected domain, what the hell does that even mean? How do you give me a simply connected domain in the first place? To a computer, how do you feed that? Now that is not an easy, that's not an easy task. I mean, how does one give a simply connected domain? One way is the following. If you have a domain in real life with a weird shape, you can approximate it. Anyway, we are doing approximations, right? So you can approximate it by means of a polygon, right? And if you take this polygon, a many-sided polygon approximates this. And if you give me the vertices of the polygon, they're all complex numbers. You can write them as u plus iv. These are real numbers. You cannot give real numbers to a computer. You can find, so you can truncate the decimal expansion to a finite number of pieces. So all these approximations. So if you give me the vertices of such a polygon in this form, then the aim is to find, and given any point in this polygon with rational coordinates, I want to find the image of this point under the Riemann map, the image of this point with arbitrary precision. That means if I want it up to precision epsilon, I should be able to do it very quickly. Okay, so this is what it means, the question of finding an algorithm. If we want an algorithm, Riemann proved his mapping theorem more than, so when did he prove it? Probably more than 150 years ago, I think. We need to put in a lot more work if you want an algorithm. The best such algorithm was found only 10 years ago by Chris Bishop from Stony Brook University. So the Riemann mapping theorem, if you actually want to implement it in practice, you need a nice algorithm. The best such algorithm was only found a decade ago. Okay. In the facial recognition problem, you remember at the very beginning I said if I want to recognize faces from a list, I would want to map them to each of these by means of a nice map and see to which I can map them, right? Unfortunately, typically we want to take a bunch of points. We would want to take the eyes to the eyes. We would want to take the nose, maybe this point on the nose and this point on the nose to this point on the nose and so on. We would want to take maybe the tips of the lips and a few things like this to this and so on, right? We would want to take a bunch of points to another bunch of points, like the tip of the nose, lips, etc., to another bunch of points. This is not possible by conformal maps in general. The reason is if you fix remember that the Riemann map is not unique. There is some freedom, but the freedom is very restrictive. There are only 3 free parameters at your disposal. Okay. If you fix 2 points, Schwarz's lemma says that that map is determined. So in other words, this is not possible by conformal maps in general. The best one can do is to use a generalization of conformal maps. Conformal maps preserve angles between curves. So one can allow angles to not be preserved, but we want them to be distorted as less as possible. These are called quasi-conformal maps. We want the best possible quasi-conformal map. Okay? So that's the thing in the facial recognition problem. And quasi-conformal maps play an important role in pure mathematics too. But these things are typically not covered for students, but I find it useful and nice to mention because it's quite interesting. All right. So the problem is the proof of the Riemann mapping theorem is so difficult that not only do I not have time to do it, I'll be surprised if you will do it for your students too. I mean, I don't know, but nonetheless, I'll just give you a brief idea of Riemann's original proof because it is so very pleasant. There are several proofs of this theorem. In a slightly special case, which is what Riemann considered, where the domain has a nice boundary, that is things like this, as opposed to things like this. Okay? One can do it using some ideas of physics. This is why I like this proof. Riemann's interesting idea was the following. That is, suppose you imagine taking the domain and you put a positive charge somewhere here. If you're familiar with electrostatics. So what happens is the lines of force, and imagine putting a positive charge and grounding the boundary, meaning you connect the boundary to the ground so that it has zero potential. So the electric lines of force will look like this. They'll be perpendicular to the boundary. They'll look like this. And the places where the potential energy is a constant, they'll all be perpendicular to these electric lines of force. They'll look like this. So the boundary has electrostatic potential 0. Inside the domain, the potential obeys the Laplace equation. And near the charge, it behaves like so. Don't worry about this. The equipotential lines, in other words, the places where the potential energy is a constant, right? These are electric field lines. These are equipotential lines. You can map these equipotential lines to these circles, and you can map these electric field lines to the radial lines. So this polar coordinate grid becomes this grid. Okay, so the electric field lines are perpendicular to the equipotential lines. Using simple connectedness, one can map these to radial lines of the unit disk. This is where simple connectedness comes into play. Okay. So Riemann assumed that the Laplace equation can be solved without proof because he thought, I mean, this is just physics, right? I mean, he said, okay, in real life, this will happen, so maybe it can be done. But that's not true. This actually requires a lot of work. But Riemann did not do that work. But anyway, nonetheless, this is a rough idea of Riemann's proof. I had another proof also another idea of another proof and some other concept called Schwarz's reflection principle. But honestly, I don't think it makes sense to cover them now. I think I'll stop at this point. So if you have any questions.
So sir, why we are interested in solving Laplace equation only, means what it indicates?
For example, the Laplace equation plays a role in electrostatics because, I mean, if you take say, not really. Okay, let's say you take an insulator and you tell me what the potential is on the boundary, and you want to know what the potential is here, then it's also the Laplace equation. Maybe like a conductor, for example, and take the potential on the boundary. Actually, not a conductor, an insulator. And one more place where it plays a role is if you take a hot plate, okay, and you allow it to cool down, after a long time, the temperature will solve the Laplace equation. Another place where it comes into play is in fluid mechanics. I don't exactly remember the physical problem in fluid mechanics. I mean, it has to do with these things called vortices. I mean, suppose you go to North India, you go to the Bias River, you'll see it's very dangerous out there because of these tiny whirlpools. Or if you go to say Vijayawada and look at the Krishna River or something. These things can also be modeled, if I remember right, I could be wrong, by using the Laplace equation in some way. There are pure mathematics reasons also to solve the Laplace equation, but these are some of the real world applications. Any other question?
Sure, there is one more result called reflection principle. So just tell only statement and only some rough idea about this. What is
so the reflection principle is basically, the point here is to answer this question. When can Riemann maps extend across the boundary? That is, suppose I have let's take a very simple case. Suppose I have the upper half plane and I have a holomorphic function from there to C. Okay, can I find a holomorphic function on all of the plane to C that extends this? That means, can I find a new function which, when restricted to the upper half plane, equals f, and here it is somewhere else? Can I always do this? The answer is no, you can't always do it. But Schwarz's reflection principle says that if you have a continuous function on the closed upper half plane, such that it is holomorphic, it is analytic here, and it is continuous till this part. Suppose f takes the real values on the real axis. It takes real values on the real axis. Okay, so it takes the real line to the real line. Then it extends to the entire plane as a holomorphic function. This is Schwarz's reflection principle. The way it does is you simply reflect it, in the sense that if you give me a point here, it goes somewhere here. You just take z bar, reflection, and you take it to precisely f. If you want to find where this point goes, you reflect it. If you have z here, take z bar. You take this to some point and reflect that point also. Okay, so you get this function. The point is that this function is actually holomorphic. Okay, so that requires some proof, but the point is, this is Schwarz's reflection principle. Why do you care about it? Because it tells you, suppose you have some nice kind of domains. What kinds of domains I won't tell you, but certain kinds of domains, if you give me the Riemann map, I can extend it across the boundary. I can give you a map that is defined on a slightly larger open set. That's why.
So actually it is extension of the map from upper half plane to the whole complex plane.
Yeah. That can be done provided it takes the real axis to the real axis. And you do it by reflection. That's why it's called Schwarz's reflection principle.
Sir, when you say that, when we are doing Dix minus non-negative axis, and You give some explanation about its simple connectedness. Can you, sir, explain it again?
Simple connectedness. Oh, that one, disk minus that, right?
Yeah, sir.
Okay. Let's see where. Okay, I don't. Damn, I was hoping I already had. What I'm saying is, if you take the disk minus the non-negative real axis, there's a conformal map that takes the hemi-disk to this, right? Z square. Okay. So it's a one-to-one analytic map, and the inverse is also one-to-one and analytic. In particular, it's a one-to-one continuous map. The inverse is also continuous, right?
Okay.
If I give you any loop in the disk, you can use this inverse to make it into a loop here. This one is already simply connected because it is convex. That is, you can write a formula for this type to shrink it to a point. And you take this shrinking by means of this, and you can get something here. In other words, you can use this formula here, and you can compose it with this function to get a formula here.
Okay.
Okay. Any other questions? Right? There are no others. Then I'll stop.
Sir,
Yeah.
sir, is conformal map, every conformal map is homotopy equivalence? So because that conformal map is homotopic equivalence, how to show that, sir?
No. What do you mean by homotopy equivalent? Homotopy equivalent to what?
Sir, means two of the domain and range. They are homotopy equivalence always, sir.
No. Is your question, is every conformal map homotopy equivalent to some map? If so, what is it?
No, sir. Actually, that is deformation retraction, no, sir? Inverse of that
Okay,
thing.
so what is your question then?
Sir, means every conformal map is like deformation retraction, or it is something else also?
Deformation, no, but deformation retraction to what map? That's my question. Deformation retraction is between two maps, right? So you're saying a conformal map is deformation retracts to what other map? The question is not clear to me. Yeah.
Yes.
In any case, the point is, if it is from a simply connected domain to the unit disk, then yeah, so if you take a conformal map from the simply connected domain to the unit disk, well, any two such conformal maps are deformation retracts of each other because they differ by a Mobius map. And you can connect Mobius maps to the identity. But anyway, that's that. Any other questions?
Sir, there where you have written the Modulus theorem, there was only one problematic point.
What? What was the problem?
Yes, this slide.
Mm-hmm.
So I was asking how to show integration f over gamma, where gamma is any triangle is 0.
Yeah.
Here 0 was the only problematic point, and we were approximating such a way that the integration becomes smaller.
Yeah.
Now, if there is some more problematic point, let's say 2 or 3, then will that process work?
Any if you have finitely many problematic points and the function is continuous, in fact, this is a theorem of Riemann that if you have any finitely many problematic points and if a holomorphic function is continuous at those points, then it's actually holomorphic at those points. And the same proof works. Any other questions?
So if there are no questions, let us thank Professor Vamsi for a very, very interesting talk. And I really enjoyed.
Thank you.